For decades, calculating the product of two large matrices was bound by a strict computational limit. The classical divide-and-conquer approach requires executing operations at a cubic time complexity, mathematically expressed as O of n cubed. This cubic scaling exists because of how matrices are partitioned. When you split a matrix into smaller subsections to compute them recursively, the standard method forces the computer to execute exactly 8 multiplications for every single split. This diagram shows the specific mathematical constraint Strassen targeted. By engineering a method to compute the exact same matrix using only 7 recursive multiplications, the structural limit shifts. The 8 becomes a 7, dropping the entire algorithm's complexity down to O of n to the power of 2.807. Moving from cubic time to a subcubic scale of 2.807 dictates how fast a machine can process data. As matrix dimensions stretch into the thousands or millions, this specific reduction shaves countless processing hours off of massive datasets. To understand exactly how Strassen eliminated that 8th multiplication, we have to map his 7 algebraic equations, run a pure numerical test on a generic dataset, and analyze the asymptotic trade-offs of his model. What we find is that achieving high-level mathematical efficiency requires abandoning brute force arithmetic in favor of abstract recombination. We start with a standard mathematical objective, finding a result matrix, which we will call C, by multiplying matrix A by matrix B. The first step of the divide-and-conquer strategy requires slicing both matrix A and matrix B into 4 equal quadrants, scaled at n over 2 by n over 2. We label these submatrices 11, 12, 21, and 22 based on their spatial positions. In the classical method, calculating just the first quadrant of the result matrix, C11, requires multiplying A11 by B11, multiplying A12 by B21, and adding those two products together. Because finding C11 alone demands 2 distinct multiplication operations, scaling this process to find all 4 quadrants of matrix C inherently forces the computer to run 8 separate multiplications. To bypass this limit, Strassen introduced a set of completely foreign intermediate equations that restructure the data before the multiplication step even occurs. The core engine of Strassen's approach relies on generating 7 intermediate products. We denote these as M1 through M7. This formula display shows the first trick. Instead of multiplying single submatrices, Strassen adds or subtracts specific quadrants first. M1 is found by adding the diagonals of matrix A, adding the diagonals of matrix B, and then multiplying those two sums together. M2 is calculated by taking the sum of the bottom row of matrix A and multiplying it by the top left quadrant, B11. M3 isolates A11 and pairs it with the spatial difference between the 2 quadrants on the right column of matrix B. M4 flips that logic. It isolates A22, pairing it with the difference between the 2 quadrants on the left column of matrix B. M5 requires summing the top row of matrix A and multiplying that total by B22. M6 returns to the first equation structure. It combines the spatial difference of A's left column multiplied by the sum of B's top row. Finally, M7 takes the difference of A's right column multiplied by the sum of B's bottom row. These equations demand a high volume of addition and subtraction operations. However, by accepting that structural sacrifice, Strassen restricts the most computationally expensive operation, multiplication, to exactly 7 steps. M1 through M7 are purely intermediate fragments.
On their own, they are mathematically useless until they are structurally combined to output our result matrix. To find our actual result quadrants, C11 through C22, we execute a recombination phase, relying strictly on the M variables we just generated. This equation shows the assembly of the top left quadrant, C11. It is constructed through a precise mix, M1 plus M4 minus M5 plus M7. The adjacent quadrants are more direct. C12 requires only the basic addition of M3 and M5. C21 requires the addition of M2 and M4. The final quadrant, C22, mirrors the complexity of the first, requiring M1 minus M2 plus M3 plus M6. A theoretical framework is only valuable if it perfectly maps to raw data. We need to run a numerical proof to verify equivalence. Let's input a 2x2 dataset. Matrix A contains 1, 2, 3, and 4. Matrix B contains 5, 6, 7, and 8. We map these numbers to their spatial variables. The top left of matrix A, A11, is 1. The bottom right of matrix B, B22, is 8. Substituting these into the M1 formula, we add 1 and 4, and multiply that by the sum of 5 and 8. That simplifies to 5 times 13, giving us an M1 value of 65. For M2, we add 3 and 4, and multiply by 5. M2 is 35. M3 is 1 times the difference of 6 minus 8, yielding -2. M4 is 4 times the difference of 7 minus 5, which gives us 8. M5 requires the sum of 1 and 2, multiplied by 8. M5 is 24. We conclude the intermediate calculations with M6, solving to 2 times 11, which equals 22. And finally, M7, solving to -2 times 15, yielding -30. These 7 distinct values hold the structural code of the final matrix. They just need to be assembled. With the M table populated, we initiate the final recombination phase. We calculate C11 by substituting our M values into the formula: 65 plus 8 minus 24 minus 30. The result is 19. C12 is -2 plus 24, yielding 22. C21 is 35 plus 8, giving us a value of 43. We find the final quadrant, C22, using 65 minus 35 minus 2 plus 22. The output is 50. Our resulting matrix is 19, 22, 43, 50. If we take those exact same starting arrays and run them through a standard 8-multiplication classical algorithm, we can verify the output. The results are identical. Strassen's 7-step process maintains flawless mathematical equivalence while explicitly removing one recursive multiplication. Removing a single recursive multiplication operation from the base of the algorithm tree compounds heavily as the dataset scales up. This split screen diagrams the formal recurrence relation for Strassen's method. When we apply the master theorem to solve it, the complexity mathematically binds to O of n to the power of 2.807. This translates to a substantially better asymptotic time complexity. As the dimensions of the matrices increase, the gap between cubic scaling and 2.807 scaling widens, allowing Strassen's algorithm to completely dominate standard multiplication in raw processing speed. However, the algorithm carries strict overhead penalties. The intermediate formulas are memory-heavy, and they demand a vast increase in the volume of simple matrix additions and subtractions required at every D and C level. Because of this overhead cost, applying Strassen's formulas to very small matrices is highly inefficient. At small scales, a computer's hardware-level execution of classical multiplication is faster than routing data through intermediate addition steps. Strassen's algorithm remains a permanent landmark in computer science because it provides a blueprint for optimization. It proves that rigid computational limits can be bypassed by breaking down a mathematical fundamental and recombining it from a completely different angle.